Hey guys, today's notes is on the Doppler effect. So hopefully you've watched a few videos in class on this already, but if you haven't, you will soon. Please put today's date, title it Doppler effect, and then write down the definition. Also, just draw this picture for yourself. Oops, let's slide that up a little bit. Draw this picture for yourself. Pause it while you do that, and then we can continue. Alright, so now you've drawn the picture in your notebook, and let's describe it. The definition first of the Doppler effect is a change in frequency of a wave due to relative motion between the source, it's the source of the sound, and the observer. So Doppler effect is about change in frequency, which means for sound, that's right, we're talking about the pitch. So you could kind of write in quotes, for sound, we're talking about a change in the pitch of sound, not the volume. The Doppler effect does not describe a change in the volume, and some people get that confused. They think it's getting louder with the Doppler effect. Not happening. It's all about the change in the pitch only. And it's due to relative motion. We use the word relative because we could have multiple objects moving, or we could change which object is moving. Relative motion between the source, that's what makes the sound, and the observer, that's what listens to the sound. So in our picture, our observer is going to be a person. Technically, they're on the sidewalk. We're going to label them observer. And this person is listening to a car approach and then pass them from the left to the right. The car is beeping its horn the whole time. So the car is the source. You may have also experienced with a train that passes you when they beep their horn or whistle or whatever they call it on a train. Okay, the V stands for the velocity. So this is saying the velocity is from the left to the right and still from the left to the right after it passes. Okay? All right, so you should probably have experienced at this point that there's a sound when it goes by you of like that, and let me do it again. It's important to know that I did not change my pitch here. I kept it the same, and here after it passed, I kept it the same, but lower. The only place where the pitch changes is right when it passes the observer. Okay? The car is going to get louder and louder and louder when it beeps, because it's beeping its horn, but that's because it's getting closer to the person. That is not the Doppler effect. The Doppler effect doesn't have anything to do with the car getting louder just because it's closer, and the car getting quieter just because it's getting further away. The Doppler effect has to do with what's happening right here. Right there when they pass the person. All right? So the deal is with the car here that the car is making sound waves that travel to the person, okay? But every time the car makes a sound wave, there's one wave, crest and a trough together. Every time the car makes the wave, it takes a step closer to the wave that it just made. So now it is sort of inside the wave that it just made, and then it produces more waves. Because it steps into the waves, the waves are squished. They're squished up. And that sounds like a high frequency or pitch. But after the car passes, you can hear my pitch go down. Why? Because every time the car produces a wave, instead of stepping into the waves, sorry, I'll pick this up a little higher. Instead of stepping into the wave, the car is now stepping away from the wave. So now, I know the car isn't stepping really, it's rolling. It steps away from the waves. So the waves don't get squished, instead they get stretched. What do stretched waves look like? They look like this. What do they sound like? They sound like a low frequency or pitch. So when the car steps into the waves it's making, then you get a high frequency or pitch, but when it steps away from the waves it's making, you get a low frequency or pitch. And that's the Doppler effect. And the change occurs right here when it changes from moving towards the person and now it's moving away from the person. That's when the pitch changes. It's all due to the motion of the car. I want you now to draw the reverse diagram. Draw the car moving from the right to the left, and you could pause and take a moment to do that. All right, so title it up that the car is still beeping its horn. Number 2, we'll call it right to left. Here, copy that down. And let's look at the waves that the car is producing. Well, because it's the reverse diagram, here the car would be stepping into the waves that it makes. And you would get this high pitch on the other side now. So here, the car on the right side, because we reversed the direction, it's getting closer to the person. It steps into the waves, and it's high frequency. But here, the waves that the person hears, the car is stepping away from those. So they end up like low frequency. Oops, steps away from waves, low frequency. It's funny that even though the car goes from the right to the left, it still starts at a higher pitch and ends at a lower pitch. And the reason for that is because the car is still getting closer to the observer, okay? The car's still getting closer to them, so you get the squished up waves, even though it's coming from the other side. And when the car's going away from the person, you still get the low sound when the car is going away from the person, even though it's coming from the other side of the street. Okay, so what you really need to pay attention to is not what side of the street the car comes from, but just ask yourself one question. Is the source and the observer, the person in the car, are they getting closer to each other? Are they getting further from each other? Or neither? Are they just staying still? Staying still is easy. There's no change to the pitch. But when they get closer, no matter what direction the car comes from, the left or the right, when they're getting closer, like that is here, the waves get squished up and the pitch and the frequency get higher. So if they're moving closer to each other, no matter what, the waves are getting squished, whether it comes from the left or the right. Or I should say, here it's coming from the left. They're getting squished up because they're getting closer to each other. Here on the right side, they're getting closer to each other. So they are still squished up. But if the objects are getting further from each other, like they are here, then the waves, no matter what, will get stretched out. And the pitch and the frequency will get lower. So you just have to ask yourself that question. Are they getting closer, further, or staying still? And right here is where you hear that big change, because what happens when it passes you, that change in the sound is due to the car changed from getting closer to you to now getting further from you. So the pitch changed from high to low.